Welcome to AI Paper Slop, where we skip the fluff and get right into the most important technical research you need to know about. Today, we are tearing into a paper called ISO, an RLVR-Native optimization stack.
Yeah, this is from Hanking Zhu and a pretty massive team across UT Austin, Together AI, the Ellis Institute, and a few others.
Right. And the core insight here, it fundamentally changes how we should think about training reasoning models.
Yeah.
So right now, the entire industry is basically using pre-training optimizers for post-training.
Which is wild when you actually think about it.
Exactly. Specifically for reinforcement learning with verifiable rewards, or RLVR. This paper proves that doing that is just highly suboptimal. It turns out RLVR weight updates don't actually need to rewrite a model's weight spectra at all.
Yeah, they exhibit what the authors call spectral inheritance. So the model acquires new reasoning capabilities purely by rotating the input and output singular frames of the matrices.
Right. So by fixing the spectrum and only optimizing the frames, they built Isospectral Optimization, or ISO. And the results are crazy. Offline, their ISO merger achieves state-of-the-art data-free merging of RL experts.
And then online, their ISO optimizer matches AdamW's accuracy in, 2.7 times fewer steps.
Yeah, 2.7x fewer steps. It's massive. So to really understand why ISO is such a big leap forward, we have to look at the structural mismatch between how we currently train reasoning models versus how they, actually learn.
Right. We're taking models that have already ingested the statistical structure of the internet during pre-training.
Right. They already know everything.
Exactly. And we're trying to teach them rigorous logic using sparse outcome-level rewards, like, did this math proof work?
Right.
Or did this code compile?
And the contrast in the supervision signal there is just staggering when you map it to the parameter updates. Pre-training relies on dense token-level supervision.
Yeah, every single token gives you a gradient. It's fundamentally shaping the core representations of the model. You're building the conceptual vocabulary from scratch.
But with RLVR, which is the engine behind models like DeepSeek R1 and the newest Quinn models, you aren't teaching new concepts. You're taking a model that already knows Python, already knows calculus, and you're just teaching it how to chain those concepts together to reach a verifiable goal.
Yet we use the exact same Euclidean optimizers, like standard AdamW. We use that to translate those sparse RLVR rewards into weight updates.
Which is so weird. We treat the optimization landscape as if we're still doing pre-training. And previous research has already highlighted how strange this is, showing that RLVR Euclidean updates are remarkably sparse and off-principle.
Yeah, which creates a huge mechanical mystery. We're seeing these explosive behavioral gains going from a solid base model to a top-tier reasoning engine driven by sparse, off-principle motion in the weights.
Right, which implies that Euclidean coordinates are just the wrong lens for viewing what RLVR is actually doing to the network.
The Euclidean view completely obscures the underlying geometry. So to strip away that noise, the authors shifted to a spectral perspective using SVD, singular value decomposition.
Okay, right. So any weight matrix can be factored into three components: an orthogonal matrix U, a diagonal matrix sigma, and another orthogonal matrix V transposed.
Right, and visualizing that linear algebra in the context of a neural network layer is, I think, really crucial here.
I always like to think of the weight matrix SVD as like a giant audio mixing board in a recording studio.
Oh, I like that analogy.
Yeah, so the singular values, the sigma matrix right in the middle, those are the master volume faders for different frequencies. They dictate the raw scale and the importance of the various feature directions.
Right, and those faders get perfectly dialed in during the massive compute expenditure of pre-training. You don't want to mess with them.
Exactly. Then you have the U and V matrices, the output and input singular directions. In the studio analogy, those are the routing cables. They connect specific microphones to specific channels and then route those out to specific speakers.
That mixing board analogy perfectly sets up the empirical observation that honestly sparked this entire paper.
Right, because when they looked at standard supervised fine-tuning, or SFT...
Yeah, like taking Quinn 2.5 math and tuning it into DeepSeek R1 distill.
Right, when they did that, they saw that SFT actively alters those master volume faders. It substantially shrinks and reshapes the spectrum. I think the relative spectral residual for SFT was around 35%.
Yeah, 35%. It basically rewrites the scales of the weights completely just to accommodate the new formatting constraints of the supervised data.
But the contrast with RLVR is what makes this so compelling. When they ran that exact same spectral analysis on the RLVR transition, Those master faders were virtually untouched.
The relative spectral residual was what, hovering around 3%?
Just 3%. RLVR leaves the base spectrum almost perfectly intact. Mechanically, the optimization process just naturally realizes that the faders, the fundamental feature scales established during pre-training, they're already optimal for reasoning.
Right. So instead of messing with the scales, RLVR just repatches the routing cables. It rotates the U and V frames to connect different input features to different output features, chaining existing knowledge into new logical paths.
But, I mean, the implications of a 3% residual are profound, but we definitely have to be careful about attributing intent to high-dimensional optimization, right?
Oh, absolutely. I mean, in a model with billions of parameters, a single weight matrix might be, say, 4096 by 4096. The number of singular values is tiny compared to the total parameter count.
Which raises an immediate skeptical question. As an engineer, you look at a matrix of that scale and think, wouldn't almost any random high-dimensional update leave the spectrum mostly unchanged just by sheer statistical chance?
Exactly. We have to figure out if RLVR is actively constrained by the lost landscape geometry to preserve the spectrum, or if it's just, a mathematical artifact of living in a massive dimensional space.
Where random noise barely moves the needle.
Right, and the authors anticipated that exact skepticism. So they introduced this really rigorous calibration metric called the dimension-normalized spectrum-changing energy. They call it Kappa Spec.
Kappa Spec. And this metric isolates the energy of the update that specifically alters the singular values, and it normalizes it against the total dimensions, right?
Yeah, and the brilliance of Kappa Spec is its baseline. If a weight update is completely random and perfectly isotropic, the expected value of Kappa Spec is exactly 1.
That's perfect. Setting a baseline of 1 gives us a definitive ruler. And when they applied Kappa Spec to the SFT updates, the values just exploded.
Yeah, they're ranging from 89 to over 1,300.
Over 1,300, which proves SFT updates are highly concentrated in spectrum-changing coordinates. They are hundreds of times more focused on changing the singular values than random chance would ever predict.
But then, when they measured the RLVR updates, the Kappa Spec values consistently landed between 1.0 and 1.4.
Wow!
Yeah, RLVR sits right on top of the dimensional reference for random chance.
So that calibration proves two things at once. First, RLVR doesn't possess some magical active suppression mechanism that violently rejects spectral change. But second, it proved the contrast with SFT is undeniable.
Right, RLVR fundamentally does not care about rewriting the spectrum. The optimization naturally lives entirely in the rotational frames.
Okay, but observing a structural correlation is one thing. It doesn't prove it's the actual mechanism for reasoning. To prove spectral inheritance is real, you'd need to show the model's reasoning capabilities are decoupled from those tiny 3% spectral changes.
Right, and they executed a functional intervention to prove exactly that.
What did they do?
They took a fully RLVR-trained Model 1 that already had advanced reasoning and self-correction, and they forcefully stripped out its learned spectra.
They just ripped it out.
Yeah. They literally replaced the post-training sigma matrix with the original base model's spectrum, sigma 0, while keeping the newly learned U and V frames.
If the model's reasoning relied on those minor spectral shifts, that intervention should have completely shattered its performance.
Exactly. But it didn't. The model retained almost all of its acquired reasoning capabilities.
That is insane. That is the definitive proof of spectral inheritance. The base model's weight spectra are functionally reusable, and all the learning during RLVR is actually just stored in the rotation of the frames.
Which naturally leads to the next question. How much of that rotation is strictly necessary? The authors tested a rule they call both frames move.
Right. So they restricted the adaptation during the intervention phase, like trying to see if they could just adapt the U frame or just the V frame or even remix features only within the incoming spans.
Yeah, and I would assume just intuitively that heavily restricting the degrees of freedom like that would cause the model to lose the fidelity of the RL update. It failed spectacularly. When they restricted the updates to just one frame, it left massive unexplained residuals. Anywhere from 40% to 80% of the checkpoint change remained completely unaccounted for.
Wow, okay, so you must keep the spectrum fixed, but you absolutely have to allow both singular frames to adapt to capture the true RL update. The geometry of the policy shift demands the flexibility of both input and output rotations.
Exactly. And establishing that functional proof unlocks the first major application in the paper, which is isomerger.
Yes. We are taking this structural observation about SVD geometry and using it to solve one of the most notoriously brittle problems in ML right now, merging different expert models.
It's so hard to do right now.
Right. Suppose you take a base model, you use RLVR to train a world-class coding expert. Then you use that same base model to train a separate world-class math expert. If you try to merge those two using standard techniques like task arithmetic, ties, or TSV, you almost always get destructive interference.
Because the standard methods just average the Euclidean task vectors or do simple sign resolutions. They treat the neural network like a flat sheet of paper, totally ignoring the complex geometry of how the models actually learned.
But isomerger bypasses that interference by leveraging spectral inheritance. Since we know both the coding expert and the math expert share the exact same optimal base spectrum, isomerger just discards any noisy spectral changes the experts made.
Right. It isolates their frame changes and maps those updates strictly onto the Stiefel tangent spaces of the shared base model.
Okay, let's break down the geometry of that Stiefel tangent space mapping, because this is where the math gets incredibly elegant.
Let's do it.
The UNV frames are orthogonal matrices, which means they don't live in a flat, standard Euclidean space. They live on a curved mathematical surface known as a Stiefel manifold.
Yeah, you can picture it loosely like the surface of a sphere.
Right. If you have 2 points on the surface of a sphere, and you take a standard Euclidean average by, drawing a straight line between them, the midpoint doesn't sit on the surface anymore. It ends up floating somewhere inside the sphere.
And that is exactly why standard merging techniques corrupt the model. When you average orthogonal matrices directly, the resulting matrix is no longer orthogonal. You literally fall off the manifold, and the routing cables get completely tangled.
So to solve this, isomerger projects the expert frame displacements onto a tangent space,
Which is a flat plane that barely touches the curved manifold at the exact point of the base model's frames.
Because the tangent space is locally flat, you can perform standard linear combinations there without breaking the underlying geometry.
Right, but before they even do that aggregation, they apply a really critical denoising step. They introduce a ratio called row keep set to 0.9.
Okay, so keeping 90% of something.
Exactly. It masks out the trailing singular modes, so the bottom 10% of the modes associated with the smallest singular values. In any SVD, those trailing modes represent the lowest energy directions, which makes them highly susceptible to variance and noise across different training runs.
Makes sense. By zeroing them out, isomerger ensures it's only combining the most stable, robust routing changes from the experts.
Yep. And once the noise is masked and the updates are projected onto the flat tangent space, the combination itself uses a ridge-stabilized unit retention target.
That's a mouthful. What does that actually do?
It optimizes a set of coefficients to ensure that no single expert dominates the aggregate direction. It also prevents experts that happen to push in overlapping directions from excessively amplifying each other.
Oh, which is a massive problem. That's a huge cause of activation blowouts in merged models.
Exactly.
But wait, after you've successfully aggregated the updates in the flat tangent space, you still have to get back onto the curved manifold.
Right, you can't just stay in the tangent plane.
So isomerger uses a polar retraction to snap that combined update back onto the Stiefel manifold. It mathematically finds the closest, perfectly orthogonal matrix to your aggregated update, which guarantees that the resulting UNV matrices remain pristine.
And then you just multiply those newly merged, perfectly orthogonal frames back with the fixed base spectrum, and boom, you have your combined model.
The most impressive part of this entire sequence is that it requires 0 post-merge data. No rollouts, no gradient updates. It's a purely offline mathematical operation executed directly on the tech points.
And the empirical results really validate the elegance of the math here. The authors tested isomerger on Qwen 2.57b, combining 3 separate RL experts, coding, tool use, and memory.
A triple merge. Nice.
Yeah. And they also ran it on DeepSeek R1 Distill 1.5b to combine coding and math experts. In every single scenario, isomerger outperformed orthomerge, ties, and RAM.
But the most revealing metric wasn't just the average score, right? It was the stochastic decoding performance.
Right. They measured the worst-case stochastic decoding, or the worst at 4 metric.
This is a critical nuance for production models. If you ask a model to generate 4 different reasoning paths for a complex math problem, worst at 4 measures how poorly the model performs on its absolute worst attempt.
Yeah, it's essentially a proxy for reliability and consistency.
An ISO merger uniquely and significantly improved this worst-case performance compared to the baselines. It didn't just smash the capabilities together, it integrated them in a way that made the resulting reasoning highly consistent.
Achieving that level of reliability offline is a massive win for model deployment. But, and this is where it gets really crazy, the paper doesn't stop there.
Right, they push it further.
Yeah, they push the geometric theory to its absolute logical conclusion. If keeping the spectrum fixed and rotating the frames works perfectly for merging models after they're trained, we should theoretically be able to bake that exact constraint directly into the optimization loop during RLVR.
Which brings us to ISO Optimizer. This takes the offline geometric theory and forces it to run live during the forward and backward passes. And the logic is just wonderfully straightforward. If the spectrum shouldn't change during RLVR, we should stop letting the optimizer waste compute and inject noise by trying to change it.
Exactly. So ISO Optimizer takes a standard base optimizer, like AdamW or Muon, and confines its search space entirely to the singular frame variables, U and V.
Well, the base spectrum, sigma, is completely locked from step 0.
And constraining the search space strictly to those rotational frames yields staggering efficiency gains. The authors trained a Quinn 3.8b base model using standard AdamW, and it reached an aggregate accuracy of 0.495 after 270 training steps.
Okay, 270 steps for standard AdamW.
When they swapped out the standard optimizer for ISO AdamW, the model hit that exact same accuracy of 0.495 in just 100 steps.
That is 2.7 times faster convergence. In the context of large-scale RLVR training runs where you're generating thousands of rollouts and running massive reward models, saving 60% of your GPU time is a transformational cost reduction.
Huge reduction. And it didn't just plateau earlier either. By forcing the optimizer to respect the geometry of RLVR, the model actually kept learning, peaking at a higher final accuracy of 0.509.
The theoretical gains are undeniable, but as an ML engineer, executing this in a real training loop introduces a severe engineering hurdle.
Oh, yeah.
To optimize only the frames, you have to compute an SVD on every single weight matrix at every step of the training process.
Which sounds insane.
It sounds like a catastrophic compute bottleneck.
Yeah.
SVD is notoriously expensive on GPUs. But beyond just the speed, SVD algorithms, which rely on iterative solvers, are highly susceptible to accumulating floating point errors.
Right.
If you are constantly decomposing and reconstructing massive matrices, I would totally expect the numerical instability to completely shred the model's orthogonal frames.
And the authors actually hit that exact numerical wall. They found that if you rely on PyTorch's default FP32 single precision SVD on GPUs, it creates massive reconstruction errors.
Oh, wow.
Yeah, the floating point drift during the iterative solver just corrupts the polar retraction. They measured mean squared spectral errors around 7.7 times 10 to the negative 4.
That's way too high.
Exactly.
Yeah.
When you're trying to strictly preserve a spectrum, an error rate that high means your model will degrade into complete noise after just a few dozen steps.
So to stabilize the decomposition, they had to make a really counterintuitive engineering pivot. They switched the SVD computation on the GPU entirely to FP64 or double precision.
Right, which normally ML engineers avoid FP64 like the plague. Double precision throughput on consumer GPUs and even a lot of data center GPUs is heavily throttled compared to FP16 or FP32.
It sounds like an absolute performance killer, but the authors optimized the implementation brilliantly because they're only computing the FP64 SVD on the weight matrices and not on the massive activation tensors. The computational footprint is highly contained.
Well, and by switching to double precision, the reconstruction error just dropped off a cliff. It went from 7.7 times 10 to the negative 4 all the way down to 2.8 times 10 to the negative 8.
Wow. And that perfectly guarantees the numerical stability required to keep those frames orthogonal over thousands of steps.
But what about the wall clock penalty?
That's the best part. The actual wall clock penalty for using FP64 turned out to be almost non-existent. For a 2048 by 2048 matrix, the standard FP32 SVD took 0.89 seconds.
Okay.
The highly stable FP64 SVD took 0.92 seconds.
That's nothing.
You eat a 30 millisecond penalty per layer to guarantee perfect numerical stability, and in exchange, you cut your total training steps by nearly a factor of 3.
That is an engineering trade-off that every AI lab in the world will gladly accept.
Right.
And this FD64 implementation proves that ISO Optimizer isn't just, an abstract math trick. It is a fully realized, stable, and deployable training stack. It really highlights why you have to deeply integrate your understanding of linear algebra with the realities of hardware precision to make these theoretical breakthroughs actually scale.
Taking a step back to look at the macro perspective of this research, the journey the authors take us on is incredibly cohesive.
It really is.
It begins with a really sharp empirical observation. The spectra stay fixed during RLVR while SFT alters them heavily. Then, instead of just accepting that correlation, they built the Kappa Spec calibration to prove it wasn't some high-dimensional artifact.
Right, they followed that up with a functional intervention, literally ripping out the spectrum to definitively prove spectral inheritance.
And finally, they translated that physics-like observation into a complete mathematical stack ISO merger for pristine offline composition and ISO optimizer for highly efficient online training.
The broader takeaway for the industry here is that we have fundamentally entered a new regime of learning. We absolutely have to stop treating post-training RLVR as just more pre-training.
Yeah.
Pre-training is the phase where the model builds the spectrum. It establishes the fundamental scales and concepts of its world model. RLVR is the phase where the model learns how to route those established concepts to execute verifiable logic.
If we continue to blindly inherit Euclidean pre-training optimizers for post-training, we're actively fighting against the natural geometry of how these models learn to reason.
Exactly.
Which leaves us with a provocative question that every ML engineer should be considering right now. If we have been blindly inheriting pre-training optimizers for RLVR and just leaving 2.7x efficiency gains on the table, simply because we ignored the SVD geometry of the weights?
What else are we missing?
Right. What other pre-training artifacts are we thoughtlessly copying into post-training? Are our weight initializations, our learning rate warm-up schedules, or our regularization techniques actually holding our reasoning models back because they were explicitly designed for dense token prediction instead of verifiable outcome-level rewards?
It really makes you wonder how much reasoning performance is currently trapped inside our models, just waiting for the right geometric alignment to unlock it.
We will leave you with that puzzle to ponder. Thanks for joining us for this dive into ISO on AI Paper Slop. Keep questioning your defaults, and we will catch you next time.